Welcome to Descriptive Statistics. Imagine you are the manager of a large supermarket. At the end of the day, your cash register prints out a receipt containing 10,000 individual numbers, representing every single item sold. If you just stare at that massive wall of numbers, your brain will completely freeze and you will learn absolutely nothing about how your business is doing. Today, we are going to learn the art and science of tabular and graphical presentation. This is how we take that chaotic, overwhelming pile of raw data and organize it into neat, readable summaries that actually make sense. Now that we understand why raw data is overwhelming, let us look at how we can fix it. Think of tabular presentation like sorting a massive pile of mixed coins into separate jars. By grouping the numbers into a structured table, you can easily count and understand them. But we do not stop there. A graphical presentation goes one step further by turning those tables into visual pictures, like charts and graphs. This allows your eyes to instantly spot trends, patterns, and outliers that would otherwise remain hidden. Without these tools, statistics would just be an unreadable mess of numbers. With them, data tells a clear and compelling story. To build these tables, we use a fundamental tool called a frequency distribution. A frequency distribution is simply a summary table that divides a large data set into smaller, non-overlapping intervals called classes. It then records how many data points fall into each class. To build one from scratch, we follow a strict step-by-step procedure. First, we find the range of the data by subtracting the smallest value from the largest value. Next, we decide on the number of classes we want, usually between 5 and 15. Then, we determine the class width, set the exact starting and ending boundaries for each interval, and finally, tally our raw data to get the final frequency. This step-by-step procedure leads us to a crucial mathematical formula for determining the class width. Conceptually, if you have a certain spread of data and you want to divide it into equal slices, you divide the total spread by the number of slices. In this formula, W represents the class width, which is the size or thickness of each interval in our table. R stands for the range of the entire data set, calculated as the maximum value minus the minimum value. Finally, K represents the desired number of classes or groups we want to create. If the range increases while the number of classes stays the same, the width of each class must also increase to stretch across the wider data spread. Before we move on, let us see this formula in action with a concrete example. Suppose a teacher gives a math test to 20 students and the scores out of 50 are recorded. The lowest score is 12 and the highest is 50. We need to construct a frequency distribution table with exactly 5 classes to summarize this raw data. This will help the teacher quickly see how the class performed as a whole. First, we identify the maximum and minimum values to calculate the range. We subtract the lowest score, 12, from the highest score, 50. This tells us that the total spread of our test scores covers exactly 38 points. Now that we have our range, we continue by calculating the class width. We divide our range of 38 by our desired number of classes, which the problem stated is 5. This division gives us a precise mathematical width of 7.6. However, working with decimals for class widths can be messy and confusing when tallying whole numbers. Therefore, we always round up to the next convenient whole number. In this case, we round 7.6 up to 8. This means each of our 5 classes will cover a span of exactly 8 points, ensuring all our data fits perfectly. With our class width set to 8, we can now finalize our table. We set our boundaries starting at the minimum value of 12. Adding 8 points for each class, our 5 intervals become 12 to 19, 20 to 27, 28 to 35, 36 to 43, and 44 to 51. We then tally the raw scores into these brackets. We find 3 scores in the first class, 2 in the second, 4 in the third, 4 in the fourth, and 7 in the final class. Physically, this final answer instantly shows us that the majority of the students scored in the highest bracket, a trend that was completely hidden when looking at the raw list of numbers. Now that our data is organized into a table, the next step is to draw a picture of it. But choosing the wrong type of graph can completely ruin the message. We use a simple decision framework based on what we want to show. If we want to compare different categories, like favorite colors, we use a bar chart because the separate bars clearly show which category is largest. To show parts of a whole, like a monthly budget, we use a pie chart. When tracking changes over time, such as daily temperature, a line graph is best because connected dots show trends perfectly. Finally, to see if two variables are related, we use a scatter plot to reveal underlying correlations. Let us look at exactly what these four basic graph types look like. In the top left, you see a bar chart for categorical comparison, where the height of each bar instantly tells you which category dominates. In the top right is the pie chart, perfectly illustrating parts of a whole where all slices add up to 100%. On the bottom left, the time series line graph connects data points over time, making the upward trend visually obvious. Finally, on the bottom right, the scatter plot maps two different variables against each other. The pattern of the dots clearly teaches us whether a strong correlation exists between those variables. While graphs are powerful, this brings us to an important warning. Graphs can easily be manipulated to trick the viewer. One of the most common tricks is axis truncation, where the vertical axis of a bar chart starts at a number greater than 0. This wildly exaggerates tiny differences between bars. Another common distortion is the use of 3D effects. When a pie chart is tilted backward, the slice closest to the front appears artificially larger than slices in the back, misleading your perspective. Finally, broken axes are sometimes used to hide large gaps in data, making a slow, gradual trend look like a sudden, dramatic spike. You must always check the numbers on the axes before trusting the shape of a graph. To expose a misleading graph, we often need to calculate the true mathematical reality behind the visual. We do this using the standard formula for percentage change. Conceptually, this formula finds the absolute difference between two numbers and expresses it as a fraction of the original starting point. In this formula, P represents the percentage change. The variable V sub F stands for the final or most recent value, and V sub I stands for the initial or starting value. By subtracting the initial value from the final value, we find the raw change. Dividing by the initial value and multiplying by 100 gives us the true percentage. If the visual steepness of a graph is huge, but this percentage P is tiny, you know the graph is misleading. Let us apply this formula to a concrete example of a misleading graph. Imagine a politician wants to claim that crime has skyrocketed during their opponent's term. They publish a line graph where the line shoots up at a terrifyingly steep angle, making it look like crime has doubled. However, upon closer inspection, the vertical axis does not start at 0. It starts at 9,000 and ends at 9,100. To determine if this graph is misleading, we identify our initial value as 9,000 and our final value as 9,100. We then plug these into our percentage change formula to see if the mathematical reality matches the terrifying visual. Continuing with our calculation, we subtract the initial value from the final value to find an absolute difference of 100 crimes. We then divide that difference of 100 by the original value of 9,000 and multiply by 100. The final answer is approximately 1.11%. Physically, this means crime only went up by a tiny fraction of 1%. The graph is a classic example of axis truncation. By zooming in only on the range between 9,000 and 9,100, the creator stretched a tiny 1% increase to look like a massive mountain. If redrawn starting at 0, the line would look almost completely flat. Now that we know how to construct and analyze these graphs, let us talk about how it is done in the real world. In the modern world, nobody draws complex graphs or tallies massive frequency distributions by hand. Instead, we use powerful software tools to do the heavy lifting. In Microsoft Excel, you can instantly create a frequency table using a pivot table, which automatically groups and counts your numbers. For more advanced statistical work, programmers use Python with a library called matplotlib or the R programming language with a package called ggplot2. Learning these software tools is essential because they allow you to process millions of data points in a fraction of a second, turning raw data into clear visual insights instantly. We have covered a lot of ground today, so let us summarize the key takeaways. First, tabular and graphical presentations are the crucial bridge between raw, confusing data and clear human understanding. Second, by carefully constructing frequency distributions, we can organize chaos into structured groups. Third, selecting the correct type of graph translates those groups into pictures that instantly reveal trends. Fourth, we must always remain vigilant against misleading graphs that distort the truth through manipulated axes or deceptive 3D effects. You have now mastered the foundational techniques of descriptive statistics. Combined with modern software, you have the ability to tell the true story hidden inside any dataset.